Okay, so this is a little bit departure from the rest of the, we're really going to be talking about nuts and bolts estimation from this point on, after this lecture on, but before we do so, as I said yesterday, I want to give some background for how to use machine learning for things that aren't just prediction, that are for estimating things like the impact of giving certain blood product ratios. So causal inference, is, again, it's an entire course normally. It's got a huge literature. I give you some references of things you might want to read if you want to go into it in greater depth. So I'm going to give a pretty superficial background, but I think it's necessary to interpret the rest of the course, to have some of it. So that's the motivation. Okay, so there's, for the most part, when we do statistics, we live in this world. We have data, we have statistical assumptions, things are independent. Maybe we assume something about the distribution of the outcome, but we don't really have embedded necessarily a causal model about what caused what and what doesn't cause what and what has a pathway through something else, etc. So for causal inference, you need both the statistical assumptions. They don't go away. You still have them. But you also need some non-testable assumptions. You have to have, in order to say this caused that, I have to at least know it came before it, right? If I don't know what comes first, for instance, then how can I assert that this is what caused that, right? It's like if I have a picture and I'm trying to reconstruct a crime from a photograph and I don't have the ordering, I have to at least infer it in some way in order to estimate the impact of one variable on another. So, and really what we really want, mostly in science, and particularly it's obvious in experimental sciences, you want to know if changing conditions changes some outcome of interest or some process of interest. And so that's what causal inference is, the study of how do we assert causality in that context. There's a lot of ways to define causality. We're defining it in very, very blunt empirical terms. It's basically the change that would have happened if I intervene in a different way for the same system. Again, we went over this. Well, actually, this is the roadmap. We went over it yesterday, so I don't have to go over it too much again. But you have the you have to specify, of course, the question. I mean, when I collaborate with scientists and researchers in general, and I can't quite get what they're going after with their data, the first thing I always ask is, what experiment would you have done? Even if it's absurd, tell me, if you're trying to assess something you're interested in, tell me exactly what you have done. And that usually will get at what we're trying to find and whether I can actually estimate a parameter that gets it. It's a good way to organize your thinking in science, in empirical science in particular, and particularly with observational types of data where you didn't do an experiment. If you do an experiment, it's implicit what you're after, but if you don't, the observing data, then this is always a good question to get people focused on what we're trying to estimate so we put our energies toward the right thing. So that will lead, of course, to specify what causal quantity of interest, whether it's the impact on the mean if I change things. It doesn't have to be the mean. It could be the impact on the variability or the impact on the median. We're going to talk about means because they're easier to estimate. You have good theory for the resulting estimators. Other quantities become more challenging. Medians and quantiles, you can do it, but it's just harder. Identifiability, that's the main goal of causal inference, is to say, okay, well, I have observed data where I didn't do the experiment. I want something, a parameter that tells me something about an experiment I didn't do. Can I actually identify that from the data that I don't have? That's identifiability, right? And that's what causal inference is the science of. Then we'll have the usual things. We'll have the statistical model. It's a separate issue. And then once we've had identifiability, it'll define a particular parameter, a particular quantity of the data during distribution. Maybe it's conditional mean, maybe it's a variance, whatever it is, and then we go after that and then interpret results. Example of this is what we just talked about. You can ask different questions that will lead to different kinds of parameters. One is one I just addressed with those slides, is what happens. I want to know what happens if I don't have the manpower, the sophistication within the clinic to be able to tailor a particular blood product ratio to different patients. So I just want to know, I can only do one, I can only have one, so I want to know which one's the best on average, right? So that's a question we just addressed. If you're going to give high platelets versus low platelets to everybody, which one is better? And that results in something like an average treatment effect, right? It's the average effect across the population. That's often relevant because you can't tailor, through practicalities or whatever it happens to be. You can't always, or you simply don't have the data, you can't always try to tailor the treatment or intervention separately by person or by community or whatever the unit happens to be. But you can also ask questions like this, which will lead to a different set of estimators and possible identifiability results, which is, I don't want to know what happens if I give it to everybody. I want to know if I only give it to those that would benefit from it, rather than giving it to everyone. And that's more of a, it's called a dynamic treatment. This is called a static treatment. And this would be more of a dynamic treatment. That is, it's a rule. The rule could be, I have a certain injury severity, then I'm going to get more platelets, right? You could tailor the rule depending on the covariates. But just two examples of kinds of questions you could ask. And many more than that. So, causal model is just a way to represent all the background knowledge you have about the system. The person who sort of pioneered this field and for which you has written extensive literature is Judea Pearl. I have a reference in the back of the lecture for his book there, but he has all kinds of writings on it, among others. And you have to start asking questions, which becomes really important in the medical context. Is what are the factors that influence a physician's decisions? If you really want to do a good job distinguishing what really has an impact, it isn't just due to the fact that a physician will do certain things based on the severity of the patient. You need to know what those factors are, right? You need to know those factors that both affect treatment decisions and affect the outcome. And basically, of those, you really care about mostly the ones that affect the outcome of interest, and it could be mortality, it could be something else, right? So that's particularly important in medical care because you have this terrible treatment by indication problem. Do you know what treatment by indication is? Okay. We're going to talk about structural causal models. It's a way to represent the causal model, and it's, I think, very intuitive. It just represents reality as a computer algorithm because you have to start somewhere with some underlying model, and this is the way that you could represent it and derive all your results by just thinking of there's a mechanism that's generating this data, and I can write down, not very specifically, but in a generic way, what impacts what. So, doing things this way, as I said, sometimes going rigorously through the causality part and really trying to understand the causal model, what things are related to what, becomes very important because the identification, that is, understanding whether the data can really answer the question, can be pretty subtle. Many times it's not subtle, and it's not worth doing it. Like, I have a treatment, I have things that I measured beforehand, I have an outcome. I just know these things cause that thing, or maybe not, and they cause the outcome, but the time ordering means it's pretty obvious, right? Other things, it's much more subtle, and questions can be more subtle, like I'm interested in the impact of one thing on another thing, but not through an intermediate, right? And that's common questions people often ask about ethnicity. There's strong association of this in health, but they want to take apart all the impacts that have to do with access to healthcare and other things and see if there's any remaining component, right? So these are called direct effect questions. They have different sets of things to worry about than, or mediation would be another name for it, than questions that have to say, I just want to know the total effect through any pathway. It defines the causal question, and finally, you're evaluating whether the data and assumptions can answer the questions, right? And again, it's always going to require some assertions because many of these things are not testable by data. They may be something you can make good primary arguments about, and that's the importance. Causal inference really comes down to how well do I understand the science of this? Can I justify these assumptions? The data won't help you in that regard. because you can't test what comes first and what comes after from the data alone. And that's because, very simply, the probability of y given x times the probability of x is equal to the probability of x given y times the probability of y. Those are equal. And this one implies y comes after x. You're modeling y as a function of x, and this one implies x comes after y, and they're equal to each other. So the data is not going to tell you which one's a better fit to the data. You have to oppose the ordering. You have to say either x goes to y or y goes to x. Oops, yeah. So some of the assumptions are simply have to be, the causal assumptions have to be asserted and hopefully have a strong argument to back them up. There's endogenous variables and exogenous. This is terms used in many different disciplines, but commonly in economics and others. Endogenous means something's causing them, right? They're not just being randomized by some unknown deity. They have a relationship to other variables, right? So we have, we'll usually generally call those X or other kinds of capital letters. Sometimes you know the ordering. When you don't know the ordering, sometimes it depends on what you're estimating. It may matter, it may not, right? Again, I could have a graph that represents the relationship between my variables, and for some components on the graph, I might have x1 causes x2, but x3, I don't know. I'm not sure which way it goes, so I'll just put it both ways. And that goes like this. And for some questions I may care, this arrow will matter. If I can't assert it, I can't estimate it. But for other questions on the same graph, it may not matter, right? So it's not, the question of interest will guide you as to whether or not you have the information. The same graph can yield contradictory conclusions depending on what you're interested in estimating. So it includes all the variables you measure, and then it can include some latent variables, right? You may not measure some things, and they may be an important part of your causal model. Some variable that you think is maybe a state of the health of the patient that you don't measure directly, but you think results in other variables, so it's unmeasured. Can I still adequately can I still identify the effect of interest even though I have important variables that are unmeasured? Same kind of question. It depends on the question. It depends on the graph. Then exogenous variables are sort of the unmeasured error terms, right? We'll assume that, you rarely want to assume that one variable deterministically causes another one. I mean, if that's the case, they're essentially the same variable, right? This one's 5, there's always 5 plus 1 is 6, then they're the same variable, essentially. If I know that one, I know that one. So we'll generally assume that they relate to each other, but in some functional form, that's a function, it's a function of some form, x1 is equal to x2 squared, plus some residual error of some kind, because it's not perfect. And these things are called exogenous unmeasured errors. We'll typically, we'll assume they're not affected. They're just the residual errors. They're not affected by other things in the model. Sometimes we'll just use U to represent them all, right? We'll just say U are all this collection of unmeasured things that affect each of the variables. And we'll just represent the unknown is almost always unknown distribution of these factors by PU. We don't know they're normal. We don't typically know what they are. And for many things we don't need to know. Finally, the last component is the functions that relate them. So we'll just define them. The notation is fx1 is the function that produces x1. fx2 is the function that produces x2. Like for instance, if x1 is, let's say, fx1, and I'll just assume there's another x2, ux1, then, one example would be x1, this example, is equal to like x2 cubed plus ux1. right? So the function fx1 is just x2 squared. It just relates the two whatever variables that are related, it relates them. It can, of course, be a function of more than one variable. It could be a function of many variables, any particular variable in your system. Another convenient notation is parents. Parents are things that cause that variable. They're all the variables that have arrows of causation into a particular variable. They're called the parents. That's often convenient to be able to list the parents. And in general, we can write our structural causal models, so they're SCMs, in this way. For every j, we'll have there's a specific function that is a function of all the parents, all the variables that are coming into it, and some residual exogenous error of some kind. And that's how we relate our system. We do that for each of the variables in our system. And of course, what you choose to be your parent is your knowledge, right? That's how you put your knowledge in. It's just if I could have, an x1 to an x2 to a y, right? So x2's parents is x1. x1 has no parents. Also, I'll do this. u2 goes into here, and u1 goes into there, and y goes into there, right? So I have three sources of error that are affecting it, and then I have the other variables. x2 has one parent, which is x1, and y1 has two parents, which is x2 and x1, right? Those are the things that have arrows into y1. So I can represent this as a graph or a series of equations. They're one-to-one. If you give me the list of structural causal equations, I can convert that to a graph, because it tells me what's pointing into what by the list of the parents.
And you're doing that based on either prior knowledge or the science of it, not based on your data.
Exactly. Now there is a very advanced portion of causal inference field where they try, with other kinds of constraints, they try to empirically determine direction of I just told you can't do it. Well, it's not perfectly true. It's practically true, but there are lots of people working on ways of trying to figure out what does the graph look like if I just have data. And generally, it's really poorly identified, meaning you can't come up with a single graph. You can come up with many different candidates for graph, and I haven't seen it being used terribly practically, to be honest. But I can't say that you can never do it, because you can add certain constraints which start to be able to build the relationship just from empiricism. For us, and really practically at this point, for most people who are just worried about doing research, you're just doing it before you see the data. It's based on a priori knowledge, not the data itself. Now, the data might imply that there's very little relationship between one of them, right? If I declare this one as a function of two other ones, and I see empirically, well, as I change this one and the data changes, it just doesn't change much, you may have evidence that a certain parent doesn't have a strong relationship, but you have to at least say it comes beforehand, right? It's a possible parent.
But some of these things are not easy to, like endogenous variables. We go through, I'm an economist, so we go through tests, rigorous tests to define if a variable is endogenous or not. So how do we be,
Yeah. Well, econometrics has a longer history of worrying about this, and so they may, right. For instance, you often try to look for instruments when you're an economist. You try to look for natural experiments where you can say, even if I haven't measured things, that no longer necessarily confounds. But for now, all I'm saying is you have some process by which you figured out this graph. I'm not going over that process.
But it doesn't have to be bulletproof.
Rarely is bulletproof.
Okay.
I mean, the one time, time in medical science is bulletproof if you have randomized treatment. But even that is rarely perfect, right? You randomize the treatment, but then there's noncompliance, right? So then you've already added the possibility that latent variables are affecting things. That's never perfect, right? So, and I will say with this caveat, this is making a idealized picture of the way things are, so we can do stuff and go forward. But in the end, there's all kinds of assumptions that are built in that are not testable, and you always, the outside knowledge, outside the data, is always important. The statistics alone, empiricism cannot answer it. But at least it's a format for putting as much as you know down, and then you can do sensitivity analysis, right? You can say, okay, well, I'm not sure about this error. I'll take it out, redo the analysis, and see, do it change much? You do these kinds of things. There's no magic bullet that way. Yeah?
So just as an example, to make sure I've got it clear. So let's say your X1 was stroke.
Okay.
Could parent variables be blood pressure,
Sure.
hemostasis, the status of the vessel wall? I mean, those are so pathologically, those are the mechanisms.
Right.
So that's an example of how you would set up your
Exactly, and then you may not measure one of those, like status of the vessel wall. You may have no way to measure that. So it's there, but it's a latent variable. You have another variable, which is a proxy, comes out of it that you may measure. I don't know blood pressure. I don't know enough to say that. So when you actually start writing these down, it can be pretty complicated. And a lot of the things we measure in medicine are proxies, right? Mm-hmm. So there's an arrow coming out of the latent variable you want to that thing. It causes it, right? And so, and you're interested in that thing causing the outcome. I have to say, in general, it's hard to estimate effects of things you don't measure without pretty big assumptions. But yeah, that's exactly right. One thing, generally, the most practical way this works in observational studies is if it's longitudinal. So I measure things now, then I measure things in another time and go forward. I at least know all the future couldn't cause the past. So at least I have a time ordering, and if I don't have any way else to distinguish what comes first, then I can at least say just all these things cause this, and all these things cause that. And I do my analysis based on that. So that's a very common way to go about this practically. And again, sometimes when you exclude pathways, it doesn't necessarily lead to reduced bias, but because it involves fewer variables, it may decrease the variance. So, even getting more specific at that may not help you if you have a really big sample size. If you have a really small sample size, then getting rid of variables can help you a lot. If there's strong evidence that you think I can exclude them. And exclusions of variables in the past, that's called an exclusion restriction. Another word commonly used in econometrics. It has to do with the fact that you're imposing essentially an arrow that doesn't exist. You're saying, I don't have an arrow from this thing in the past to the future. I'm assuming it can't happen, right? But in general, you start with everything in the past can cause the future, and then you might start paring those down based on some other kind of knowledge. So why is this like a computer? Well, if I gave you, an assignment and I said, here's your structural causal model, how would you generate the data? Well, first of all, you draw a multivariate U from some distribution, some set of errors, right? So if I said use multivariate normal, you would draw a set of errors that might be correlated or uncorrelated with each other, depending on what you assume. And then for each x, in the order, I would generate it from the function that defines its mean, the f, and adding that u in some way, and I would just go forward, right? So you can simulate an entire data set from these sets of structural equation models if you knew them. Now, in practice, we never know them, right? We have to try to discover aspects of them from the data. But that's what, once I know u, and then once I know the parents of x, then that variable is now a deterministic function. It always will be the same number. That's making that assumption. That's part of our idealized world, that once I have, an f of x, let's say, and it might be a function of the past, so I'll just say parents of x and sub u of x. Once I know what the parent values are, and once I know what that is, then I'll always get the same number here. It won't change. I don't have randomness in the function. There are kind of extensions where I say, let's assume even the functions can be random, but then, it's a mess. You can imagine a process where that's true, but for now, we will assume that we could even incorporate that within some deterministic function where now the random function is part of the U and something. So that's it is in some ways an idealized version of the world, but it's a reasonable one and one we can work with and hope to make progress. It's just the same thing, right? Different words. Okay, here's just a way to do it in practice. Let's just take a particular same thing I've been talking about: platelet use, decrease mortality, or increase it. So I'll define my variable A to be whether or not you got platelets. So that's a variable of interest. I'll say W are all those sets of characteristics. So I'm just replacing X now with specific things. Like these are part of the X, right? X, you know, is W, A, Y. But these are the things like age, type of injury, heart rate, blood pressure when they come in before they're received. So I know they're in the past. And you know, it doesn't really help me in this context whether to know whether they're related to each other. That injury and heart rate and those kind of things. For the question I'm going to ask, it's not important, right? So I may not need to know that part of the graph. They just come beforehand. You know, a fully elaborated graph will tell you, you know, this comes first and that comes first of all the confounders. And that may be important if I care about some relationship among them. But I don't care about that right now. I just care about A and its relationship to Y. And then we'll just have the death with 6 hours. In trauma, most deaths occur, lion's share of deaths occur within 6 hours of the injury. So if there is death. So that's certainly not universally true. There can be deaths from other causes, but the immediate trauma caused death. What you're trying to save the patient by not bleeding to death is really that's the first 6 hours. Is where hemostasis is either achieved, often, mainly, or the patient dies. So now specifically, you know, I've got my here we go. Is that, yeah, that way. I've got my data, my 3 variables. Of course, I have to define that the fact I don't measure these, but there's going to be certain errors that result in them. And therefore, I'm going to assume that W is just a function of those exogenous errors. No other variable that causes the W's, the age, the injury type. They're essentially set in stone. Or they're not caused by anything else in the system, I should say. A is going to be just a function of those W's plus some other error, right? So I have some function. If I knew W and a UA, I would know what A is. You know, for what I'm interested in, I may not need to know FA or not, but that's going to be the underlying causal model. And then finally, Y is a function of both A and W, so both the things that occurred before right at injury and those occurred after they got to the trauma unit, the transfusion, and again, some other error. Nothing's deterministic. We're not assuming if I know those 2 things, I know for sure what Y is. We're always assuming there's uncertainty, right? Because it's statistics. Otherwise, we'd be doing deterministic models.
Alan?
Yeah.
I'm a little confused. I understand the last version very well. It's very similar to what you see in a regular statistical model where you're predicting Y from those.
Yeah.
I don't quite understand what the X means as a function of those 3 things.
X is just a notation that says here's the collection of variables in my system. Nothing else to it. It's just a vector of variables.
Okay.
That's all. Yeah. It's not, you know, there's nothing hidden in there. It's just a collection. It's just a set.
And U is your error terms, vector of your error terms.
I'm sorry, one more time?
U is your error terms.
The U are the errors.
represents
The
your
U are,
vector
right.
of errors.
And that's only because I'm allowing that if I knew, I can say that Y is only a function of W and A in my system, but that doesn't mean if I know W and A, I'll know Y exactly, because there's other things here. Now, I mean, again, you start getting, you know, diving in really deep philosophically. The fact that there's U, Y's in the first place, if I'm a Newtonian physicist, you know, and I believe everything, if I knew molecule or atom in the world, or every subatomic particle, whatever it is, and I could tell you exactly what's going to happen in the next step if I just was able to incorporate it into Newtonian physics, right? It would predict exactly where it's going to be. Then that would imply that the only reason this here is because I haven't measured everything. And of course, that's undoubtedly true. There's things I haven't measured, right, that are, so I don't know exactly. But it's also, could say there's just inherent randomness in the system, right? Many things in nature are looking more and more inherently random in the end. Whether it's a function of what you don't know or a function of inherent randomness, I don't know. It just happens to be true that we never have to know things deterministically. So that's what that represents. The fact that at the end there's a relationship, but it's not exact. So again, I could draw this, if I drew this as a graph, well, there's W, and I have UW going there, and then it goes to, and this, which is equal, right, is to FW, UW, and then there's A, and there's also UA, and this, of course, is equal to FAW, UA, and then they both go to Y, and also you have UY, and that's FYAW, UY. Right? So they're directional arrows, right? I don't have any bidirectional arrows here. Everything is ordered and goes in the order. So that's just taking these equations, and that's the graph it implies. There's no magic here. Just two ways of representing the same thing. And that's how you would do it, right? You would draw U from multivariate normal. I would generate W from whatever function. It could be, my function, my F W UW implies some multivariate normal. Maybe it's, or maybe it's just actually. Just equal to UW, right? That's another possibility. I generate random W's, and then those are my W's. Or I might transform them and send it by F, right? So it could be F is just the identity function. It just takes what you put in and gives you the exact same thing, right? And then just to give an example, let's say F A of W could be something like, the indicator that W, I'm just making this up, is greater than, so if I know W, I know mu A, if let's say W is just one thing, and it goes between 0 and 1, so I generate that, and I generate this. This is the indicator function, meaning it's 1 if the thing inside is true, and 0 otherwise. That would be an example of a function that takes those two inputs and just gives back a number, right? So anyway, when you generate this in practice, you can simulate sequentially in very simple ways. I could draw a random normal for W if I wanted to. Then I could have a logistic regression equation for A. You take the W's in, you make a logistic regression. That gives you the probability. You flip that coin, and then, of course, that will imply some UA. You don't have to generate explicitly in that case. And then once I have the A and W, I could do a linear regression model that says Y is equal to A plus W plus UY, right? Those are just examples of how you could simulate data that would match this structure. But of course, there's many infinite number of ways you could do it. And, I'm sorry, I actually just waited to hear. So this just gives an example, right? So I could have A equal some complicated linear function of the past plus some error that I generated randomly. Just, again, you're going to have to, the data will help you try to discover these F's. That's the whole point. That's where we're going to do machine learning to discover mainly the FYs, right? That's what we're going to start with. We often don't care about the distribution of the treatment itself and how to predict that. It's not really involved in the estimation of our parameter. So we almost always care about the prediction of the outcome given the past or given the covariates. So we'll use machine learning to estimate FY, right? We don't know it. And that the whole point is we probably can't constrain it by too many things, except to say it will respect the bounds of the Y and some other characteristics of the outcome. Okay, then we're going to get slightly more technical, and I'm going to go slightly quicker before we take our break because it's less important. It's just certain other complications you can add is you can make exclusion restrictions, which just is to say I can't have variables that come in the past, but I'm going to assume they don't cause A. I could have a W1 and a W2, and maybe they both go to A, let's say, but only one of them goes to Y, and this is the time goes this way, right? So this lack of this arrow here that I'm putting in, that's an exclusion restriction. I'm just specifying that I think that Y is not a function of it, even though it's in the past. That's what it is. So you can do these kind of exclusion restrictions. Sometimes they're really important in instrumental variable applications where you're trying to identify something when you don't even measure. Instrumental variables like this, I have a variable, let's say it's R, it causes A, it causes Y, and there might be a W that causes both, but I'm assuming there's no independent pathway to Y. R is an instrumental variable for the relationship of A and Y. That is, it causes A, but it has no independent impact on Y. And because that exclusion restriction that I'm assuming eliminates that. One good example is treatment assignment. That's where instrumental variables are pretty non-controversial. I could have a treatment assignment where you get a treatment, and then you could be the treatment you actually take, right? It could be I adhere, I don't adhere, and the outcome. And I can be pretty convinced that treatment assignment itself doesn't affect your health. Let's say, in some context you may have placebo effect or something, but let's assume we can ignore that. Then I can certainly assert that what treatment you're assigned affects the treatment you take. So R goes into A, and I can reasonably assume that R doesn't have any independent impact on Y, so that's an exclusion restriction. Once I know that, it turns out I can identify the impact of A on Y even if I don't measure W. Right? We're not going to go over that particular example, but that's called use of instrumental variables, and it's useful in that context. And economists are very clever at coming up with historical, natural experiments where this happens. Tax laws change and have another impact on something that it wasn't their intention, but they impact some other behavior that affects economic output or something. So they take that natural experiment. Another one example would be, never mind. There's been some interesting examples of lead exposure and things like that where they've used clever examples. Anyway, I find in public health and medicine, they're occasionally interesting and you can find them, and it's really great if you have an instrumental variable because you don't have to measure anything else. You don't have to measure any confounders. But I have to say it's pretty rare that you can assert something as a true instrumental variable in our field.
Question.
Yeah.
In this case, you can also use the intention to treat.
Oh, sure.
Right? And then.
Yeah. In other words, I could just get the relationship of R and Y directly, and that's what's often done as a default. But I could say I don't want that. I really want what would happen if everybody got A as 1 and took it, and everyone got A as... I want the impact among the compliers, right? That could be something of interest.
You want the per protocol effect, so you want to use...
Yeah, exactly. Sometimes it's called per protocol effect. Yep. But it isn't as simple as looking at the difference in Y based on A because it's confounded by W. So I can't do that and assert I have a causal effect anymore. So you have to use the instrumental effect. In practicality, this is always true with clinical trials. There's always somebody drops out or something happens, right? So where you don't always have compliance with the treatment perfectly. It's just a question of how imperfectly. Again, then you can start talking about the independent assumptions with regard to the U's themselves. Sometimes it matters that the U's are uncorrelated, or they have to be uncorrelated, so they're independent, the errors, in order to identify it. Sometimes you don't have to. This kind of thing I find a little bit esoteric, most applications, because you usually have no idea. They're unmeasured things, right? So people, in exercises in causal inference, you'll sometimes have U's that are correlated, so they're related to each other. Can I still identify the causal effect? And you can get into those exercises. They're useful to really dive into causal inference. We're not going to go over it because it's a little bit sidetracked for what this course is about. Yeah, we already talked about this. Yeah, it's a big example, right? I mean, in this case, they have this relationship with these. So these imply a certain set of structural causal model, exactly what we've been talking about, but also they allow potential correlation among all these. And you might say, okay, when can I identify the causal effect of A on Y, the average treatment effect, for instance? And that will depend on which of these arrows I believe exist or not, the arrow here or the arrow here. You can't have correlation among all of them. It's not identifiable anymore because you can't tell what's coming from what if the U's themselves are causing each other. And again, that's an esoteric exercise for the most part, a useful one, but we're not going to get into it too much. And this, again, I mentioned earlier, I mean, why this is practically often useful is simply as a tool for communication. I want to know what's your ideal experiment. That tells me how to draw the graph and tells me what you're interested in. And it's a good way to start any collaboration. These are just the steps we talked about. Does platelet reduce the reduction of risk of death from that word I can't pronounce, from bleeding to death or clotting to death? Essentially, that's what it means, one or the other. What is the intervention variable? What's the A? Well, of course, that's going to be platelets. What are the interventions of interest? That's the next question you have to ask. That will affect your parameter. Is it just platelets, yes, no? Is it the number of platelets? Is the number of platelets per body size? These are things, of course, again, these are refined not by the data. I mean, the data can influence what you can ask because you may not have the data to ask more refined questions. It's a function of the scientific question. And, of course, the outcome, in this case, death is straightforward, but like hemostasis, that requires a definition because there's no light that goes off on your forehead that says, oh, your blood's under control, right? That they have to measure it in some way. It usually has to say that they don't have to transfuse anymore. They have stability in the blood supply, but they have to record that, and you can define it in more proxies. And, again, I'm giving you idealized circumstances, but in reality, some of these variables are not trivial to define.
Difference that
there's no
you're
difference.
allowing those systems to kind of generate the correlations when you create a path. And here you're really looking at the causal framework and specifying that ahead of time.
I mean, a lot of these things like structural, people have heard of structural equation models, right? Well, these are exactly the same thing I'm talking about, except for they explicitly define the F's. They'll say F is a linear model plus an error term. Right. These are non-parametric structural equation models. So, and HLMs are just a form of a structural equation model. So I'm saying we're going to start by defining the same set of things, but I'm not telling you what the F's are because we're going to live in a world where we don't know them. And I don't know the distribution of the U's in many cases. And in many cases, I don't need to know it to identify my parameter. There can be cases where I have to know it, so I have to take a guess. For the most part, things we're going to talk about, you don't need to know what the distribution of U is in order to get the mean, right? So it's a good question. But Brad, this kind of stuff is used all over the place in different kinds of forms, like mediation analysis, pathway analysis, HLMs, mixed models are explicit versions of a structural equation model. Right. They're all in parametric form, and their parameters that result will have similar interpretations under that model being true as the kind of things we're going to talk about. I can come up with a model where the coefficient is the same as the treatment effect I've been talking about if everyone's treated versus not. they'll have the same interpretation, but it's just in that very small model, as opposed to a class like this where we don't know the model, so we're going to use machine learning, but they're analogous. Okay, so one important notion from all this is this notion of counterfactuals. This is how we start to define a parameter of interest. We've just talked about systems and how we might define them in the structural equation, but you know, I think we've gone long enough without a break, so I think I'm going to stop here. Let's take a 15-minute break, and then we'll come back and finish up this and go to super learning and machine learning. Is there any questions?
Yeah, just about the path that you drew. I'm just thinking of the analogy to path analysis, and people use HLM models.
Okay, we're at the point where we're actually starting to define things that we're going to estimate after defining the system. So, new notation, we're going to call this YA, which is called the counterfactual. The index A means it's going to be the outcome if you give level A equals little a. So if A is 0, in the case of platelets, then Y sub 0 would be the outcome if this particular patient did not get platelets, and it would be 1, Y sub 1 if they did get platelets. So it's just indexed by the level of the treatment. So in theory, in an experiment where you could actually give every level of treatment to a subject, for instance, and watch their outcome under the same conditions, the data would consist of all those Ys at all those levels. And the idea is if I could observe the outcome under platelets, reset the clock to when they arrive in their exact same state, and then not give platelets, that difference in the outcome would be the causal effect for that individual due to treatment. So the whole idea is we're going to define parameters that have to do with that experiment, which is a direct, it would be an experiment that would directly get at causality, because you control every other thing besides that intervention of interest, and any differences in the outcome would have to be caused because of that. Of course, an experiment you can actually rarely do in our fields, but in other fields, it may be possible to have the exact same conditions and in a Petri dish and give one level of a toxicant versus another and look at how the cells grow and that kind of thing. But the whole idea is we want to get parameters that sort of estimate those kinds of causal effects when, in fact, our data comes as simple observational data. And we'll refer to these as potential outcomes. Counterfactual is the same. And counterfactual, for those who aren't familiar, just means it's the outcome counter to fact had they gotten this level of treatment. So it's become more common in just parlance to speak of counterfactuals, but it's technically the definition. So basically, they're the basis. What we're going to do is use the structural equation models to generate different outcomes under different interventions on only part of the structural equations, not all of them, right? Because we're not trying to isolate the impacts of one thing at a time, or just one thing. And the way you think of this on the graph is if I have, this was my original model. I want to, so I have some Y, I have an A, I have a Y, I have errors that go into them. There's exogenous errors and then possible correlation or not. I want to look at the distribution of Y under a scenario where I just set this 1 to 1, right? There's no, I break this arrow now. So it's really, it's just 1, and I look at the difference between Y at a random A and Y at a fixed A, right? If I could do that for every subject, I could compare now their Ys at different levels of A by just carrying through, this is all theoretical. In theory, if I could carry through the structural equation model, if I had it, and just get the outcomes under different A's. And this is what it looks like in the graph. You're essentially breaking arrows, right? You're eliminating certain arrows because you're intervening and setting them. And you know, errors can be much more, the interventions can be much more complicated. It doesn't have to be fixed things. You could, instead of replacing having A being a particular value, you could have a rule. You could say, I'm going to replace A not with 1 or 0, but with a rule which depends on the value of W. If W is high, I give it 1, and W is low, I give it 0. Now look at that effect, right? All these types of interventions will be specific to different questions, and they all can be addressed by this framework. So in order to define the parameter that you're ultimately going to try to estimate, you know, obviously you have to define which variables on the graph you want to intervene. And also, again, it doesn't have to be just one. You can investigate counterfactors that are indexed by 2 treatments. I could have a treatment that has to do with blood pressure, a treatment that has to do with cholesterol, and I may want to know the outcome if I intervene on both simultaneously. Both have the drug, you know, let's say 2 hypertensive drug and a statin. I could look at the probability of stroke or the outcome of stroke. Yes or no. If you have both drugs, neither drugs, one, the hypertensive drug and no statin, and the no hypertensive and the statin, or vice versa, whatever. All those combinations, right? So it doesn't limit itself to asking just questions about intervening on one node. You can do multiple nodes, and I can start talking about intermediate nodes, like I'll intervene on this drug but block some action that it does. So I have 2 nodes I'm intervening, both on the drug and on possibility of cutting off some pathway, you know, that it might affect. So it can get quite complicated, right? It's very general. It can handle many different types of experiments. And again, then you have to define on what interventions you're interested in. Maybe there's circumstances where I'm really only interested in what would be the outcome under the lowest risk value. If I'm doing public health stuff and I have risk factors, I really want to know, like, what would be the impact if I cut air pollution down to a certain level? So I want to know what is the, and the outcome might be asthma. So what would be the asthma if I put this person to no exposure to air pollution? I did that for the whole population. That may be enough, because then I could just compare it to the current distribution of the outcome, and that would be the change I would get in this population had I intervened. So it doesn't always, you know, you can compare different counterfactuals at different levels. You can compare counterfactuals to just the current distribution. There's all kinds of different comparisons, and that will be a function of the question you're after. And then, of course, you have to decide how to relate the different counterfactuals. Do I want a ratio of the means, a difference of the means, an odd ratio? You know, I could have, you know, let's say E y1 over E y0. That's one parameter. I could have E y1 minus E y0. That's another. You know, you just have to decide how you want to represent it. This is somewhat arbitrary, but again, it will depend on what you think best communicates the impact. It doesn't really change the interventions in this case. It just changes how you report the resulting means. So again, as an example, you know, again, same thing, risk factor platelets. I'll talk about outcome is either hemostasis or death, both binary, same structural equation models I'll assume, and the errors. And then now I can define something called the full data. And the full data is the data I wish I had to answer the scientific question. This is really how, again, if I go back and working with collaborators, it's like what would you like to have done? That defines the full data, meaning this theoretical data set you wish you had if you were able to intervene exactly how you need to do to be able to assess causality directly from the data. See, if I had all the counterfactuals, I wouldn't have to do anything fancy, right? I just take the mean of the y1s and the mean of the y0s, and that gives me the difference in the means. I don't have to model anything, right? So the whole idea is an experiment that leads itself to a simple estimate of the causal effect without any assumptions, is what you're getting at. So that's the full data. And the reason why this is sort of interesting, you know, is that causal inference, the estimation of causal effects, is really treated as a missing data problem. You're just missing one of these, right? And so the same techniques that you might use for missing data, imputation, inverse weighting, there's other ones, come into play for this. You're just treating it, everyone's missing one of the counterfactuals. If there are two of them, they only get one. And you can use exact same methods developed for missing data in more standard context to estimate causal effects, because you're essentially missing something and you want an unbiased way to sort of impute the value of the outcome had you had the treatment you didn't get, and similar kinds of assumptions follow. And that was really a function of both represented this way is really Jamie Robbins to some extent, and then Mark Vanderlyn and Richard Gill, another theoretical statistician, showed you could treat these problems as a missing data problem, and you don't, if you do so, you don't really constrain the answers at all. It doesn't really impose any constraints on what the estimate will look like. So it's not an important, it's a practical way and a theoretically convenient way to treat this problem. And at the end, one of the most common kinds of parameters that people get at are the so-called average treatment effects, ATE. So, you might have heard things like propensity score matching or inverse weighting, or other estimators, G estimation or G computation. And we're going to talk about those at some level. They're all ways of trying to estimate this parameter of a distribution of data you don't have. You have an observed data which doesn't contain the counterfactuals, but this is the most common parameter. It doesn't, again, there's no magic about it. It's a convenient one. It's often a convenient way to represent the distribution of counterfactuals or the mean of them. But again, there's no objective reason why you wouldn't look at a ratio as opposed to a difference. And that's what, you can have this is called, also causal. Well, if y is binary, it'd be causal risk difference, and then you could have a causal relative risk, which would be, E. Sometimes I put the subscript for the expectations. That just means under what distribution. You have to take an average over some population. That tells you which population. I just sometimes leave it out. Just put expectation. It's implied, but it's like.
So I have a question.
Sure.
When we apply like the traditional regression modeling for average treatment effect,
Yeah.
I usually do like bootstrapping because they're counterfactual, not real observation, to estimate the standard errors.
Well, the reason, if I have a linear, let's say that the true model, the true FY, the FY of A and W, let's say I assume, which of course, the class